Hello everyone, my name is Shihao Chen. I'm from UT Austin. Today I will present our work Pangolin, an efficient and flexible graph mining system on CPU and GPU. Graph pattern mining is to discover patterns of interest in a given input graph. A pattern is a template subgraph that is defined by the user. It captures the subgraph structure. These are the patterns that need to be found in an application called motif counting, such as triangles and the cliques. Another important term is the embedding. An embedding is an occurrence of a pattern in the input graph. It includes actual vertices and edges of the input graph. In this example, the pattern is a triangle, and there are two embeddings of this pattern in this input graph. To solve a GPM problem, one way is to implement a dedicated solver by hand. Here I list several GPM problems and their corresponding handwritten solvers. Handwritten solvers are time-consuming and error-prone to develop. Also, the programmer needs to deal with parallelism on modern parallel architectures, which makes programming even more difficult. The good thing is, the programmer has the flexibility to control every detail of the mining process and apply all kinds of optimization techniques. Handwritten solvers usually achieve high performance at the cost of lots of engineering effort. To improve programmability, many GPM systems have been proposed. Here I list several representative GPM systems. They implement common functionalities for different problems and provide simple interfaces to the programmer. Meanwhile, the systems take care of the parallelism, and the user only needs to write operators for each embedding in a sequential way. The user program is then transparently parallelized on the targeted platform. However, as I will show later, existing systems are not efficient. Many of these systems are orders of magnitude slower than hand-optimized solvers. Motivated by this, we propose Pangolin, an efficient and flexible GPM framework. It is easy to code and transparently parallelized on the CPU and the GPU. It provides flexibility to the user to compose their own optimizations. It is also highly efficiently implemented on both architectures. As I already mentioned, existing systems are not efficient. This is due to, first, many application-specific optimizations are missing in these systems, such as search space pruning and avoiding graph isomorphism tests. Second, in these systems where parallel operations and data structures are inefficiently implemented on today's parallel hardware. Due to limited time, I will only talk about the first part in this talk, and you can find details about the second part in the paper. Pangolin overcomes these limitations. It provides a simple and flexible programming interface to enable application-specific optimizations. The interface keeps the simplicity as previous systems do, and exposes more flexibilities to the user to apply optimizations. Pangolin applications are automatically parallelized to exploit underlying hardware, such as multiple CPUs and GPUs. Pangolin is the first GPM framework that supports GPU mining. Parallel operations and data structures are efficiently implemented for the targeted architecture. Overall, our system achieves orders of magnitude speed up over existing GPM systems. To solve a GPM problem, Pangolin uses a simple execution model called extend and reduce. Here I use an example of counting triangles. Starting from each vertex of the input graph, 1, 2, 3, and 4, we iteratively extend one more vertex at a time until the pattern size is reached. So in the next iteration, we get all the 2 vertex embeddings. We can notice that there are some redundant embeddings. For example, these 2 embeddings, 1, 2, and 2, 1. We call them automorphisms. Since they are identical, we only need to keep one of them and discard the rest. We used an automorphism check to pick a canonical one out of all automorphisms. When the size of embeddings are the same as the size of the pattern, it comes to the reduction stage. We check each leaf embedding, and if it is a triangle, we increase the total triangle count. In general, to identify if an embedding is isomorphic to a specific pattern, we need to perform an isomorphism test. Here is an example that shows how to implement motif counting in the Pangolin framework. The programmer only can use an API function called toAdd to apply the default automorphism check provided by the system. Overall, this motif counting implementation is as simple as those in previous systems. In comparison, the state-of-the-art handwritten motif counting solver has more than 2,000 lines of code. To achieve high performance, the Pangolin programming interface exposes some details of the mining process, and therefore the user can apply search space pruning to avoid unnecessary enumeration and replace expensive graph isomorphism test with simple checking logic. Here is an example of pruning. In this example, suppose we want to find a pattern of 4-click. At the 3rd level, we only need to extend the triangle. There is no need to extend the other 2 embeddings because they are definitely not going to be a 4-click. This is the Pangolin user code for k-click listing. To implement the pruning in Pangolin, we need to only implement 2 API functions, toExtend and toAdd. In comparison, the handwritten k-click listing solver has almost 400 lines of code. Note that previous systems do not expose the toExtend API function, and therefore their users cannot implement this optimization of pruning. We evaluate Pangolin on CPU and GPU using 4 GPM applications. These are some of the labeled and unlabeled graphs we used in the experiments. We used the patent data set to show the results in this talk. More results can be found in the paper. We compared the performance of Pangolin with previous GPM systems, Arabesque, RStream, and the Fractal, all on the same CPU platform. The figure shows the execution time in log scale. Lower is better. Due to the optimizations like search space pruning and avoiding isomorphism tests, as well as efficient parallel implementations, Pangolin consistently outperforms existing systems. On average, we observed 49, 88, and 80 times speed up over Arabesque, RStream, and the Fractal. For some applications such as 3 motif counting, Pangolin is orders of magnitude faster. Pangolin even achieved competitive performance with hand-optimized implementations for many cases, significantly reducing the performance gap. Pangolin also supports GPU mining. Thanks to our efficient implementation for the GPU architecture, we can further speed up GPM applications by 15 times over on the V100 GPU compared to multiple CPU. To conclude, Pangolin is an efficient and flexible GPM system. It provides a simple and flexible API to enable application-specific optimizations. It is efficiently implemented to exploit modern parallel hardware. Compared to hand-optimized implementations, Pangolin provides much better programming experience. Compared to existing GPM systems, it's order of magnitude faster. Thank you.